um, Avalara R&D. She's going to talk about concurrency, actor model, and Akka. Over to you.
Hello, good evening, everyone. So today I'll be speaking on concurrency, actors, and Akka. Firstly, just to gauge the audience, how many of us have worked here with actor model or have some intuition about it? All right. So this would basically be an introduction to the actor model and how can we code in an actor model, the advantages of it, etc. So why is it important? Firstly, because today we deal with a huge amount of data. Today we need to build microservices to cater to thousands and lakhs of requests simultaneously within a second. So it is upon us to build applications and systems that can be concurrent and distributed. There are many ways to do this, and one of which I'll be showing today. A little background about me. I am a software engineer at Avalara. Previously, you might know it as Index in Chennai. I have been here for 2 years now. I have worked across different teams. I mainly worked in Scala, Spark, Hadoop, Akka, Elasticsearch, so distributed systems. And recently, I shifted into an ML role where we are building an ML-based solution for a classification problem. So just to give you a brief agenda for today, firstly, I'll start with why even talk about concurrency or actor model. What are the issues that plague the modern systems? Then we'll see what is the actor model, some core concepts of the actor model, modeling. Once we know what an actor model is, how do we realize it in code? Then we'll see Akka introduction. Akka is a popular toolkit for implementing the actor model. So we'll be seeing that. Then Akka actors in a concurrent world. Now that we know what actors are, now that we know what Akka actors are, we'll try to build an application, a concurrent application using Akka. Then we'll also try to build a distributed application that is a MapReduce problem using Akka. And finally, I'll be telling you about the best practices of while coding, while making an actor model, and also the shortcomings of this entire system. So to start with, I'd like to get you all acquainted with this example, which we'll be seeing it throughout the session. So take this as an isolated system. There's a bank, and there are 10 accounts, each initialized with $100. And these accounts can transfer X amount to each other. They can withdraw some amount, they can deposit some amount, etc. So take this as a system. What is the invariant here is the amount in this isolated system will always be $1,000. I hope we are all clear with this. So this is an isolated system which has a bank and multiple accounts which can do transactions. But what is an invariant which should always remain true is that this system should have $1,000. If account A transfers $10 to account 2 and account 2 transfers it to account 3, the overall balance of the system will still remain $1,000. So now that we know the problem statement, let's just try to analyze the challenges that we can face while building an application as simple as this. Firstly, encapsulation. It's a very popular concept borrowed from object-oriented world. Encapsulation basically enforces two things. Firstly, protection of invariance, and secondly, information hiding, which basically says that an object state is its own. No other object can modify it. No other object can directly access it. It can only be accessed via some curated methods provided by that class itself. So what could happen? What could go wrong in terms of encapsulation in a concurrent application such as this one? Say account 1 wants to transfer $10 to account 2, and at the same time, account 3 wants to transfer $10 to account 2. What we are seeing here is a multi-threaded environment. What could actually happen here is a corruption of state. The state, which is the balance of account 2, might get corrupted. if not properly handled. So this is one challenge. So this is a scenario in a multi-threaded environment, which brings me closely to my next challenge, which is concurrency. As we all know, concurrency is a very important concept and very essential in building microservices today. So the challenge, concurrency firstly is basically when two tasks start and end at the same time. They may not be running at the same instant. So here, as you can see, as I told earlier, there could be when two accounts try to make a transaction at the same time. So in this scenario, uh, we might have to implement some coordination between the threads, because there's a shared resource called balance that needs to be synchronized. So we need some coordination between the threads that we have various ways of implementing using semaphores, logs, mutexes, etc. So this is one way, but it's a dangerous way because there are many challenges associated with logs itself. Firstly, logs are not very easy to implement. This is a very simple application, but in a production level application, when you want to synchronize, you need to be aware of the resource creation you're doing with respect to logs, mutexes, etc. Secondly, logs are expensive. Because of the context switching, the constant caller method to callee method execution switch, and so on and so forth, it takes a toll on it adds a lot of overhead to the overall execution of the application. So logs themselves are very expensive. Third, code readability. As a developer, when you're writing code infested with logs and mutexes, you need to be very aware of each and every level. What is the critical section you're targeting? How are you handling? Are you handling it in a proper way using logs? So logs can be hacky as well, because you can run into conditions like deadlock, live lock, etc. I won't get into that right now. So now that we've talked about concurrency, another very closely related issue is parallelism. Parallelism is when tasks run at the very same instant. So think of concurrency and parallelism as two aspects of the same problem. Concurrency as an aspect of the problem domain, wherein your application should handle the ability to cater to simultaneous tasks. Whereas think of parallelism as an aspect of your solution domain. It would be great. You would want your application to be split across multiple processes which can be run parallelly. So these are both important concepts, but have different uses. So again, parallelism is a challenge here, because if you say you want to deploy different parts of the same application on different machines or different processes, that is basically parallelizing it. How do you do it? How do you assure synchronization? We have a concept of distributed logs, but difficult to implement and also difficult to scale. How do you go about solving this? Resource management. In a multi-threaded environment, when you have multiple concurrency-related resources and multiple, say, logs, mutexes, and open sockets that you're using, you need to be aware of all of these, and you need to be aware about the resources you're using. You need to be aware if there's no memory leaks. You need to be constantly aware of that as a programmer, so as to increase the efficiency of your program. Failure or fault tolerance. This especially comes in from the environment of distributed systems. When you have distributed systems, there you are bound to have some failures. For that, you need to have some sort of fault tolerance. Say one node goes down in your cluster. And coming to a more granular level, what happens in a concurrent application? What if one of the thread goes down? What if one of the thread is terminated? What if it throws an exception? Will the caller method, which pass the context to the callee method, will it be notified that some error has occurred? Maybe there's some other process which depends on this thread for a particular outcome to perform a particular function. So how do you model this situation in a multi-threaded environment. So here are some challenges that we saw using this simple example. So let's see a small demo. My screen is visible, right? Yeah. So yes. View. Wherein? Sorry? Oh, yeah. Thank you. So as you can see here, this is a simple program of the same scenario that I described earlier. Suppose there is something called an account. For the sake of this application, we'll have a state called balance, which is mutable. There are functions associated, deposit, withdraw. And then there's an entity called bank, which has X number of accounts, which deals with 10 number of accounts as we saw in the diagram. Its function is to initialize the accounts, that is give some initial balance to each account, say $10. Then transfer. A bank can act as a mediator between 2-3 accounts to transfer money. Bank can get system balance, that is $1,000, the whole balance in the system. And finally, we have a transaction class, which is the main class. Here, what I'm doing is it will randomly do some amount transfer. So let's see here. So as we see here, I have randomly initialized 10 threads, which will, in a given span of time, will transfer X random number of dollars from account X to Y. $9 from account 1 to 7. So in this particular case, the amount in account 1 would be $90. And sorry, $9, right? So $91. And in account 7 would be $107. But the total balance in the system remains $1,000, which is what we want. But if you go on and see here, what's happening here is the total balance decreases. So there's something very visibly wrong here, because the system should have a consistent amount of balance. Where did that money go? So what's happened here is a classic case of corruption of state. So how do we solve this problem? Firstly, now that we've identified the problem that two threads tried to access a balance simultaneously, this is what the issue happened. Let's try to solve it. Scala, this program is in Scala, and Java both have primitives to synchronize your application. So let's try one of those. Synchronize, simple primitive. What it'll do is, what it essentially says is, it says is only one particular thread can access this section at one instant of time. So therefore allowing the state to not be corrupted. To verify this, let's run this again. Yes. Now that we see balance is 1,000 throughout, it is very well maintained. Easy. Why don't we just use synchronized everywhere? So as you can see here, this is one instant transfer. Say what if I also want to synchronize my withdraw. Say an account which wants to withdraw balance from the bank, I also want that synchronized. I'll end up adding a synchronized block here. And same with deposit. So we can't keep doing this, because essentially what we are doing here by adding synchronized blocks everywhere is making it blocking. It is as good as a serial application. You are wasting your resources. You are not able to leverage the power of whatever resources you have. So as I said, implementing lock and realizing where to implement it's tricky. All right. So now I come to the actor model. Now we've seen challenges. in terms of theory. We've seen in code what could go wrong and what are some corner cases. Let's see what an actor model is. So actor model, I'll give a very small, easy example to visualize it firsthand. Think of yourself as an actor. You are living in a house with a mailbox. Every now and then you go and check your mailbox. Your relatives, each of your relatives send you letter. So you'll pick the letters from the mailbox one by one. And on picking, you'll decide what to do with it. One of your relatives write, "Hey, how are you? Remember to feed the cat." And you, as the reader of that message, can now decide, hey, to reply back to them, "Hey, I'm good, how are you?" B, to go feed the cat. Or C, do nothing about this, just throw it in the trash can. So you, as the reader of that message, can decide what to do with that message. After you're done doing whatever you wanted to do, you'll go and read the second message, so on and so forth sequentially. This in its entirety is the actor model, as simple as that. We have a bunch of actors, each of whom have an internal state. And each actor has something called a mailbox, and the actors pass messages to each other. So the three important parts or the primitives of an actor model are actor, message passing, and the execution environment. I'll talk about them in detail. Actor. Now, an actor is a fundamental unit of computation which has three basic principles, which is storage, processing, and communication. An actor, as an entity, think of actor as an entity whose only purpose is to talk to other actors or do something with itself. So talking about an actor has an address. You can not access an actor directly. You can access it through its address. Say I, as an actor 1, I want to talk to actor 2. I can talk to the address of actor 2. This address may not be a unique identifier because actors might be behind a proxy of actors. State, each actor. Now this is a very important primitive of actor which builds the whole actor model. State. Each actor has a state associated with it, which is basically the internal variables of that particular order. Think about our bank example. One account could be one actor and its balance would be its state. So these two terms we have correlated with the theory of actors here. Now, what's special about this state is the state of an actor is isolated. It's not shared. It cannot be accessed by any other actor. It cannot be mutated by any other actor. So it is mutable only by the actor himself. As account 1, I can only mutate my balance. No other account can come and mutate my balance. So this is a very important property of the actors in the actor world, which we'll see how this is very important in implementing concurrent applications. Next, an actor has behavior. Like I said, when an actor receives a message, it can choose what to do with it. It can A, create more actors, it can send messages to other actors, or perform some computation. This is the behavior of an actor. Mailbox. Each actor has a mailbox associated with it. This is where the messages of the actor are lined in. Every other actor sends messages to other actors, and those messages will be lined up in the mailbox of their actor. So what is message passing? Message passing is the communication between actors through messages, as simple as that. It's just some information that is passed between messages. Asynchronous. It is asynchronous, non-blocking. Actor model is based on the philosophy of fire and forget. That means, as an actor, I can send you a message and then forget about it. This is very important because we can contrast it with, say, a shared state model, where there's a caller thread which calls a callee thread and it is blocked until the callee thread is finished. Its execution is done. So this is a very contrasting feature in our actor model. The messages that are passed between actors are immutable. Say if as an actor I pass message to some other actor, say value of X is 10. The other actor cannot change this message. It can only do something about this message. Maybe it can update the copy of that variable in its state, but it cannot change the value of this message. Actor model works on at most once delivery or best efforts delivery. You can see it of think of it as our concepts in TCP, UDP. They, in this case, they guarantee only at most once delivery, meaning our messages can be lost. This is a feature implemented very uh, by knowledge in the actor model, because they want, as the user or the developer, to handle the guarantee of the message as you want it. At least once, exactly once, at most once. It's up to the developer. But in its core, actor model has at most once delivery. Order is not preserved. When actors send each other messages, say 1, 2, 3, you may not receive it in the same order. You may get it in 3, 1, 2, or any other order. So this is something that actor model doesn't provide. Execution environment. So it's the engine that runs all actors. We saw a bunch of actors sending messages to each other by reading it from their mailbox. So who schedules these messages? Who schedules which actor gets the execution context right now? That's our execution environment. Think of it like the execution context in Java, Scala, or any other language. So coming back to our bank example, we'll try to see how the same example can be realized in terms of an actor model. Same thing, there are multiple accounts here. Each account has, and there's a bank account, there's a bank. All of these are actors. So the account 1, 2, 3 have mailboxes, and so does the bank. Say account 1 wants to transfer some account to the bank, or withdraw some account from the bank, or transfer some amount to account B. It needs to send messages to it. This is what it would look like. As you see, the messages sent by these actors are queued in the mailbox of the bank account. Easy to understand. So actors send messages, say deposit, withdraw, and they're all queued up in the mailbox. And the bank actor reads them one by one and executes them. So how does all of this having an immutable state and asynchronous communication, the two important properties of actor model, how does it solve the problems that we saw initially? Let's get back to them and see how it helps. Encapsulation. We realized that the encapsulation was a challenge in concurrent systems. So encapsulation is basically data hiding. But actor model dictates that the state of an actor is immutable and inaccessible to any other actor. Hence, we have inherently maintained encapsulation. Eliminates race condition. Since there are no locks, there's no simultaneous access of a shared state. There's no race condition. Resource management. Again, since there are no concurrent resources as locks or some sockets, we do not need to worry about opening, closing, or terminating them. It's all handled beneath the structure of the actor model. Exploit modern CPUs. Since it helps in building concurrent applications, one most important feature is actors, like millions of actors can be spun on like dozens of threads without even your knowledge. So this is how actor model within its internal structure helps in exploiting the power of modern CPUs. As a user, as a developer, you won't be faced with the challenge of optimizing your memory allocation. You'll just be spinning more and more actors to tackle your situation. Immutability. So the very reason languages like Haskell and Erlang, Scala are popular is because of immutability. Since there's immutability throughout your code, you do not need to be worried about where state might get corrupted, which other thread might corrupt it, or etc. So it's as a developer, that's one thing less on your head. Fault tolerance. Like we saw, actor model is based on the philosophy of let it crash. What happens is if an actor dies, it's all right, the whole system won't be terminated. And this is achieved through a number of ways. To give an example, one way is when an actor is terminated, there would be a supervising actor which will tell the caller actor, hey, this actor that you spun has terminated. So what do you want to do about it? Secondly, the supervisor actor could restart this actor, give it another shot. So there are various ways by which you can handle fault tolerance in an actor world, which is very important. And finally, distribution. So now that we know that actor is just a piece of code with a mailbox and a state, an internal state, and passes messages to each other, it doesn't matter if it's on one machine or multiple machines. Actors can be spun across different machines and continue communicating to each other through addresses. So that solves a very important problem and helps us distribute our application. So some contrasting features with our classical shared state model. The state in a shared state model is shared. Actor model, it's isolated. That's a very important feature of the actor model. A state of an actor model, of an actor, is isolated from other actors and immutable by other actors. Secondly, communication. In a shared state model, it's through method invocation. There's a call stack that's maintained and the execution is transferred from one function to another, etc. In actor model, message passing. Synchronization. In shared state model, locks, mutexes, semaphores, etc. In actor model, none. Because actor model by principle itself handles asynchronous behavior. So that's very important and it makes it very easy for a developer. Control flow, mostly synchronous because otherwise we need to implement it. Actor model, asynchronous. In shared state model, it's called shared state concurrency. In actor model, it's called message passing concurrency. So Akka here. Akka is a very popular toolkit which is used to realize the actor model in code. Now we know the challenges with traditional shared state model. We saw what an actor model is. We also saw how an actor model could solve those challenges. Now we want to see in code how it looks like, how can it solve those problems. So Akka is like a vast toolkit. It has a lot of sub tools available. What we'll be using here is just the actor model within Akka. So just to draw some correlation with the actor model we saw, Akka is basically the same. It just has some APIs that can help us write an actor model in code. Firstly, Akka Actors are event-based. This is a very important property because what we need today in our application is not to be data-driven, not to be a state-driven, but event-based. Say, when this transaction is successful, do this. When this withdraw is successful, do this. Instead of saying, deposit this amount or withdraw this amount. So this is an important property. Hierarchy. They maintain a hierarchy. As you can see here, how the Akka actors are implemented is there's one main root actor, which is responsible for all the other actors spun out of it. Then there's something called a system actor, which is responsible for daemon processes and the under the hood threads required for functioning of the actor system. Then there's something called user actors, which are basically created by us. Any actors created by the user for any functionality are called user actors. So these are basically subtasks. Akka actor system. I hope we all remember the actor diagram that we saw there. Very similar to that, it's this. There's firstly a sender actor. It sends a message to some other actor. And as we saw, an actor is accessible only through its address. So something called an actor ref, the reference of the actor. So the sender sends a message to the reference of the actor. These messages are enqueued in the mailbox of that particular actor. Then there's something called a dispatcher, that is the execution environment. From the execution environment we saw, it will act on the mailbox. It will say, hey, I see this actor has some messages piled on. Let's execute this. So it will pass control to this actor, and this actor will dequeue its messages one by one for it to do some processing on it, some computation on it, or some send other actor messages. So that's up to that actor, the behavior of that actor. There's something, an isolated entity called a supervisor, which will monitor all of these. Like I talked about fault tolerance. It will see if an actor has failed. It will carry out some function based on that. So let's see a quick demo. Okay, so we'll see the same banking example in Akka. So this is done in Scala. How it works is, just how it works is, yeah, there are what, as discussed, the actor model depends on messages instead of the data. So here I've defined a bunch of classes or case objects which are basically messages: deposit, withdraw, transfer, withdraw success, create success, etc. So there's something called an Akka account. So every actor firstly extends an interface called actor, which is provided by akka.actor. Yeah, akka.actor. So it extends this actor, which means this is an actor. Each actor, as we saw, has an internal state, which is this balance. Now, Akka actors, how they work is every actor implements a method called receive. What this receive does is, it is like your mailbox. It's going to receive the messages. Now, based on the message you receive, you can define the behavior of the actor. That's exactly what we saw in the theory of our actor model. So say it gets a get account balance. It's going to tell the sender, hey, this is the balance. So Akka has a concept of ask and tell. This symbol here means tell. And this symbol here means ask. So here it says when get account balance, the account actor will say to the sender, this is my balance. In deposit, it will change the internal state of its balance, that will whatever amount he wanted to deposit, and then send back to the sender success message. So if you see here, it's like a to and fro communication here. If account 1 asks account 2 to deposit something, it will tell, hey, deposit this amount. It will change its own internal state and send back the message, hey, I've deposited so and so amount. So as you see, the same problem that we saw initially, we modeled it in the way of messages to be communicated. Case withdraw, same thing with withdraw. Then there's the bank. Again, this is an actor. It will have a function called receive. It can get a message. If it receives a message called create account, it is going to create an account and initialize it with some $100 that we saw. Then it will tell the system, yes, account creation has been succeeded. Transfer. So get account from, what it will do here is the bank, it will take the money from account X and withdraw from account X and deposit to account Y. So it is exactly what's happening here. It's an ask operation. It will say, hey, get from this account, withdraw this much amount, and then if it's successful, then deposit it. If it's failed, then say transaction is failed. So as you see here in actor model, it seems quite verbose, but it has helped us handle a lot of cases that might have been neglected or difficult to handle in a lock environment. So same way as you see, each of these is an actor and they just pass messages to each other and they mutate their own state. Finally, this is a transaction actor, which defines an execution context, like we saw. It will do a transfer operation, which is basically saying transfer X amount, Y amount, etc. Then there's a main which function, which defines something called an actor system. This is an Akka API. You can just say system is actor system and this. Then you can create an actor using this system.actor of and define the class you want to create an actor of. Now I've used awaits here, but any of us who are aware of Java futures, Scala futures, we can use on complete or other things. Just for the sake of simplicity, awaits here. What it does, it tells it bank asks to create account 1, deposit initial amount 10. Same 2, 10, 3, 10. We initialize 4 accounts. Now I'm randomly here transferring from asking the bank to transfer from account 1 to account 2, $9, so on and so forth. Let's see how this works. So for the sake of simplicity, I've shown just 4 accounts here. So as you see here, transfer $9 from account 1 to 2, balance maintained, 3 to 1, balance maintained, so on and so forth. And the last transaction, which was this, transfer amount 9 from 3 to 1, it failed. Because maybe account number 3 doesn't have the required balance. So we send a failure message. Also notice that the last transaction is appearing at the top, which as stated, the order of messages is not maintained in an actor world. It is upon the developer to maintain it on their own. So we've seen the same banking application being implemented using threads and now implemented using actor model, which seems very easy because you're just basically passing messages, telling each actor what to do rather than doing it yourself. So now that we've seen the implementation of actors using Akka in a concurrent application, now let's move to the next step, which is building a distributed application. And the simplest example for this could be a map reduce problem. Just a quick walkthrough of what map reduce is. It has 2 main stages, map and reduce. There's a shuffle stage in between. Say I have a file with a bunch of lines and a bunch of words. I need to find the word count. There's a splitting stage, which will split it line by line. There's something called a map stage. For each partition, it will find out word and the frequency of the word. Deer one, bear one, river one, etc. So in each partition, we'll get word and that frequency. There's a shuffling stage where the data is shuffled from one partition to another to get all the words, same words in one partition and different words in different. Then there's a reduce stage, which will finally aggregate the count in each partition. As you can see here, bear becomes 2, car becomes 3, deer becomes 2, river becomes 2. And then there's the final result, which is finally aggregating all of this into one file. So this is a map reduce application. This is a distributed simple example, word count example, which can be distributed. So I'll show you here how to implement this using actor model and how to do this using Akka. So these are my two files here. Say in a folder, you could have multiple files, but these are my two files here. Yes, sorry about that. Anyway, so the same map word count application, we'll try to write an actor-based application using Akka. First stage, mapper, which implements an actor. As an actor, it will have a receive method. What it can do is it can receive a message called process file, and then it can just split it into lines as we saw. Then it can send to the sender something called a mapper output, which is basically the count list, like we saw there, deer 4, or deer 1, river 1, etc. Map is the app. This is the process file. Sorry, map is the method which will basically process these words and append a 1 to every word. So basically, giving frequency of 1 to every word. Now reducer could again have would again have a receive method where it will do something. It could receive a message called word group. So as we saw, it will group all the words, the same words together in one partition. Then finally finally reduce it. What it was it would aggregate the count, say deer 1, bear 1, etc., and all the partition it will aggregate to a given sum. This is what reduce method is doing here. This is our yeah, this is our main class. So it can receive a message, say process directory. As I showed you, my directory had two files which had different words in it. So it will just do something called a process file and get the words, read the words from each file. Mapper output, it will call the mapper actor that we saw and map the word in each file to a given frequency. If it receives a message called reducer output, it will aggregate the frequency of those words. Now this is my main object, distributed map reduce. Data path is this. It will create an actor system, and then it will create the main actor, the parent actor of all of this, called the map reduce framework, which was basically at this application. It will send to it the message process directory. It's going to go here, and yeah, it's going to go here and yeah, process directory. If the map reduce framework receives a message called process directory, then do this. If it receives mapper output, then do this. So this is what it'll do. And finally, when we run this, so what we get here is each word and the frequency of that word amongst all the files that were there in the directory. And finally, we can do something like 85 words found. So here we saw a simple map reduce application implemented using actors in a distributed environment. It's important to acknowledge step by step from where we came from a threaded model to an actor model in concurrent system, an actor model in distributed system. So helps us realize and be more confident about building distributed systems, concurrent applications using Akka or any other actor framework. Now, there are some best practices associated with building an actor model. As you saw, actor was basically passing messages to each other. But there are certain things to keep in mind in terms of design while implementing an actor model. Say, firstly, actors should be event-driven and non-blocking. As we saw, both of our applications were event-driven. When the balance transaction is successful, when the deposit is successful. So all of these were events and actors acted on these events. They were non-blocking. After, say, transferring $10, the actor could do something else. It doesn't have to necessarily wait for that actor to finish up. That's an important property. Passing immutable messages. As we saw in the property of actors, it's an important feature that we pass messages and not values. As we saw in banking example, there's each actor pass messages like, hey, transaction is successful, hey, withdraw was a failure. It did not pass any amount value or something that could be changed. So as a developer, when you're designing your model, designing your application, you should make sure that your communication is immutable. Secondly, do not send behavior within messages. Do not tell, when you're talking to some other actor, do not tell them what to do. Just tell them, just give them a situation and define in that actor what you want to do with that. Like we saw, if send a message to account to the bank that, hey, deposit has been successful. Now it will itself go and do some withdraw, do some updation of balance. That's up to the bank. But you as a sender actor cannot affect the behavior of the receiver actor. There are also some shortcomings. Till now we've seen how great the actor model is in solving all the challenges we saw. There's also some shortcomings in the actor model. Firstly, survey cost. When actors are passing messages from one actor to another, from one machine to another could be, there's some serialization, deserialization overhead involved. That is up to the receiver and sender to handle. Secondly, overflowing mailbox. Actors send messages which are stored in a mailbox. It could happen that an actor, which is maybe a very important actor, receiving like thousands of messages. And we know that actor cater to each message one by one. So it might take a while for the actor to get to the end of the queue. So this is a challenge, but it can be solved by spinning more actors, and there are other such ways. Third, we also saw actor model says at most once delivery. So it says that you can lose your messages and the order of your message may not be preserved. This was consciously done when creating the actor model, because so as to make it cheap, so as to make it useful for the so as to make it useful, so as to leave it to the user to handle it on their end. Say to ensure at least once message delivery. As a receiver, you can implement something like a three-way handshake that we thought that we know about, something like an acknowledgement. You can implement that. To ensure ordering, you can have like a checksum bit at the end of your message, and the receiver side, you can just check if the checksum matches. So these are some things as a user you can handle it at your end. Actor model is not trivial to test, because as you saw, it can be confusing because there's a lot of communication happening. But once you get the hang of it, you'd realize how easy it is to write. and probably then write it in a legible way to be able to test. Yeah, that was it from my side. I'd highly recommend this a video, a very casual talk by Carl Hewitt, who's the father of actor model. It's on Channel 9, Microsoft Network, Going Deep. So it's a very informative series in which he talks about actor model being like inspired from a physics model. Like we studied about finite state machines. So he talks about how he got that sort of behavior into the computer science world to help solve the problem of concurrency. Then for Akka, the official documentation is more than enough. It's very vast and very informative. So as a beginner who wants to implement some concurrent application, you might want to start with a ping pong application using Akka. So all these examples and many other things are involved in the documentation. All right, thank you. Any questions?
If an important actor got crashed for some reason, so there we are maintaining some state, right?
Yes.
So where there could be a supervisor actor who could manage, who could restart the fresh actor to serve to cater the request. So what happened to those states, like where they're getting stored and how?
Okay, that's a very good question. And it's a kind of an advanced concept I didn't want to get into, but you can check out Akka documentation. What Akka, especially how it would handle it is, there's, as you said, there's something called a supervisor actor, which will keep a check. There's a concept called death watch. Very eerie term, but it is what it is. What it means is that we a separate actor who will be constantly monitoring all the actor or whatever actor you say context dot watch dead watch actor 2. So it will be constantly polling with that actor. So say for some reason this actor dies, what the system would do is immediately replace the mailbox of this actor with the system mailbox. So this mailbox is called the dead letters mailbox. So what happens here is any other actor who tries to send message to it will now be sending messages to the system mailbox, which is the dead letters mailbox. So the integrity, your messages won't be lost by principle. They might get lost because of the behavior, but they won't be lost. They would be aggregated in your dead letters mailbox, and then the system can spin up another actor. The system can try to restart this actor or any other supervision strategy that you define. Meanwhile, the system will also go and notify the sender actor that, hey, you have sent this message. By the way, this actor is dead. So until it restarts it or creates a new actor. So this is one way that Akka handles this whole situation, making sure that the state is not lost, your messages aren't lost, and they can be recreated. Also, the mailbox, there are various ways in which you as a developer can handle this. Say your actor might crash. So you can have like a persistent storage for your mailbox alone. Actor you can run on your memory, which may or may not survive once the actor terminates. So that particular memory is reusable. But your actor, if the mailbox in a persistent stage, the persistent storage, the system can point some other actor to that mailbox. So these are some common ways by which actor model or Akka provides you the benefit of maintaining state.
Okay, thank you.
So actually, a few things sparks with me. So how is this differ from PubSub model?
Sorry?
So PubSub model, right? The publish subscribe model.
Oh, right.
So it's whatever talk, right? You talked about immutability. So how it's differ from PubSub model and this one? So do you people really integrated in the real-time scenario? Then you got this, you implement this Akka model and distributed system, and you aggregate the result and you process it. So that's how my query.
Yeah. So as I said, it is one of the ways of doing many things. You can also have shared state model. You can have atomic variables. You can have logs and all for coordination. So firstly, the main purpose of actor model, it does help you in concurrency, but its biggest benefit over even this publisher consumer model is it will have it will give you the benefit of isolated state, which is very important. What it wants to imply through it, a very object oriented concept is maintaining encapsulation, that an actor's state is within itself and out of the bounds from other actors. So this is what the main focus is. So in terms of concurrency, it has many other like you said, variants and many other ways, but these are some of the other benefits that it helps. Say for example, a simple counter counter increase problem, you can implement it in actor, you can implement it in shared state model, you can use futures, as simple as future to implement it. But what you don't get there is the power of isolated state. It'll be very difficult in, say, like a future scenario to implement the counter increase, decrease, or maintaining of that counter variable. So this, by maintaining a sort of replication, actor model, it's one way to do that.
Okay, so as an enterprise, your company actually they are using this model to. So you told me about initially about the ML jobs, right? Told them about the Spark ML.
Yeah, yeah.
So you people are probably using Spark, some with the Spark streaming.
Yeah, yeah.
That are you implementing this model, or are you using the existing model that is implemented already there?
Very different things, because Spark we use for processing, like Hadoop MapReduce. Akka, we use it as a tool for our event-driven system. One of our systems, I'll give you an example, it is event-driven, where we constantly use Akka and Akka and Scala. What we do here is we'll have like an event bus, and it will carry all the events. Hey, trigger this pipeline. Hey, create this data location. Hey, do this. So there'll be actors for each of these tasks, and these actors would then have a behavior.
So this is implemented the Spark Summit jobs.
Spark Summit jobs. Yeah, sort of. So what Spark Summit jobs would be within the behavior. So each actor would be, say, I'm a pipeline create actor. In my behavior, I'll be like, oh, I've received a message to create a pipeline. Now I'll do a Spark dot whatever Spark Summit create this pipeline. So these are all. We use like a plethora of tools to implement some system. So Akka is one part of it, solving the problem of building an event-based system, a concurrent system.
Also, so what about so when it comes to benchmarking, right? What about the benchmarking of using Akka model while transferring data in a distributed system?
Yeah, so benchmarking, as you might have seen, I've done some sort of benchmarking, time-based, latency-based in my distributed system. So traditionally, it depends on your application, firstly, but traditionally, actor model could be a little high on the higher side of latency, because there's so much communication happening, there's so much replication happening. But at this point, what you can be assured of is integrity of your data. Nothing is corrupted. So taking a hit for your on your latency a bit is still better, I would say.
Okay, thank you. Anybody?
Hi.
Hi.
So you showed an example where you're creating an actor system. So that's going to be, I assume, on one machine, right? So in reality, we want to distribute it. So your distributed map reduce is over many machines.
Yes, yes.
So what is involved in that? And like, do you create it the same way, or is there some additional jars you require or something?
You create it the same way. Just what the only difference here is, I just say create this actor, and then I'll give you an example. Say, yeah, user ref. To user ref, send a message called, hey, process this file. So just replace this user ref with the IP or your process ID or something like that. So basically, what we are saying here is you can just have this application distributed across your many machines, and they can be easily accessible. Do your network configuration and have the IPs and the process number and the jar, of course, which is running there. So, or have all the actors running at the same time in all machines. Just have like a ref which points to the address of that actor on that machine. So just as simple as that, you can run the same application.
So yeah, when you think about it, right, because when she said distributed, I found it very difficult to implement because we build and destroy containers as frequently,
Yeah.
So if we need to build an actor system, we need to have something that is sort of fixed. And from that, we have to build other containers for,
Yes.
so putting a IP address is not really a practical solution. So I was just wondering, like, how do you do a multi-system?
You have like jars of this same application running across. As a user, you would probably not be, you can have like when you have, say, a cluster which is distributed across machines, you would also have a cluster manager which would be handling propagation of these tasks to, say, XYZ machine. So it is not in your application. When I say IP, I'm just giving an example that how it's communicated with the other actor. But as a user, you don't have to manually go and add it, because your orchestrator, your cluster manager itself would be handling resources to certain nodes. It will have the context of the application, the jar running on that node, and it could also point it to that direction, whatever task it is. So
Okay,
each actor event bus would be carrying these messages, and each actor could read from these messages, could read one message from the event bus and act on it. Now, as a developer, you don't care about what actor is reading your message. What you care about is your function being implemented. So as a user, you don't have to worry about which actor reads which message. The event bus and the orchestrator take care of it. You just need to implement the behavior of any actor on receiving that message.
Okay, so your concerns, like for example, I think you said at most once delivery and SERDE,
Yes.
these will generally be applicable only to distributed systems, right? Because from what I understand, SERDE is not really relevant for in-memory actors.
Yeah.
Right, and the same thing for at most once delivery. It's if it's in memory, it's definitely going to get delivered. So those two are referring to the distributed.
Mostly yes, and also it is a concept of the actor model. But say Akka, it guarantees at least once delivery. It also guarantees message ordering. So these are some out of the box features which you get with different implementation of actor model using different toolkits. I think Rabbit and Q, I'm not sure, is another variation which does this. So yeah, there's these are situations in distributed applications, but there are ways to tackle these.
Thank you. Anyone else?
Yes, correct. Yeah, no, actor model doesn't do. Like, it's a concept of the actor model. It doesn't do order preservation. It doesn't guarantee message delivery. But Akka, it's a toolkit implementing the actor model. It has made things easier for us as the user. So they provided as a feature to guarantee at most once delivery. Under the hood, these actors that we see, they manage that. They also guarantee there are ways through which we can guarantee the ordering of the message. So Akka can provide you those functionalities. All right, thank you.